Okay, we're back, and I just want to give you a couple more examples of normal subgroups to play around with. Think about the center, Z of G, of a group is always normal. Okay. And for that one, just go back to the definition and you'll know why this is always going to be normal. That subgroup will always be normal. And A sub n is a normal subgroup of S sub n. So we talked about it in when n is 3, right? We looked at that example, but see if you can prove in general. Okay, so the last example that we're actually going to prove is let H be a normal subgroup of G, which is a group, and K be a subgroup of G. Okay, so K is just a subgroup, H is a normal subgroup. Then HK, which is equal to HK, such that H, little h is in big H and little k is in big K, is a subgroup of G. Okay, and you should try to see if you can prove this on your own first and then come back to the video. Welcome back if you left. So now let's prove this. Okay, we're going to use, remember, to prove something's a subgroup, we have different tests. We're going to use, I can't remember which one it is, but it's the one where we show that it's non-empty and then the element and then the inverse of that element composed together is in there. Okay, so first to show it's not empty. Well, they're both subgroups, right? And so the identity element, which is E, we can rewrite as E dot E, will belong to HK. And so there is our proof that it is not empty. Now we need to, let's set up some things. And so now we're going to, so let's say this. Let's say we have two elements in HK, okay? And of course, like I said before, when you're doing proofs, if the elements take a certain format, it's always nice to rewrite them in that format. So we're going to rewrite A as H1K1 and B as H2K2. You guessed it, very good. Okay, where H1, H2 belongs to H and K1, K2 belongs to K. Okay. So now we're going to show that A, B inverse needs to belong to HK. Okay, so I can't remember which number. I think it was maybe the one step. It's probably the one step, I think, subgroup test, since we're just doing one step outside of proving that it's not empty. All right, so let's show that. So we need to think about what B inverse would look like. Well, because it is still in G, right? So we know B inverse exists, right? So since B belongs to, no, that is not what I want to say. Since B equals H2K2, then B inverse is equal to H2K2 inverse. And we have that sock shoe property. One of those properties where K2 inverse equals K2 inverse H2 inverse. Okay. So, I think I want to do this. I don't know if I'm going to have room, so let's start on the new page. So, AB inverse equals H1K1 times K2 inverse H2 inverse, which equals H1, and then using the associative property that we have with groups. Okay, and K2 inverse. Okay, and this will equal H1 H prime. And I know you're like, where is this prime coming from? Okay. Which actually proves our proof. Because once we prove, okay, because now we've just shown that this is an element of HK because of closure. But I know the question is, well, where did you bring this H prime in? So let's break that down. Or if you're clear with it, then we're good with the proof and we're done. But if not, let's sort of break this down. Well, here's the thing. I'm going to, just for simplicity's sake, I'm going to let X equal K1, K2 inverse. Okay. Which of course belongs to G. Okay. Remember, we're assuming that H is normal, and we haven't used that fact in this proof yet. And it's important because if H isn't normal, you can assume when you have two subgroups of G of a main group that when you put them together, it's going to also be a subgroup. Okay, so be careful. You can't assume that. But if it's normal, you can. And here's why. So I'm going to rename that. So from that part here, what we have is H1. Actually, I'm going to go back to this step. So if I rename it X, so it's going to be H1X, H2 inverse, right? Now, if we look here, because it's normal, what this is saying is that there is an H. Oh, I called it H prime. So there's an H prime in H such that H prime equals, okay, so through the magic of technology, I erased that part because I found, I think, a simpler way to explain this. So we're still going to let X equals K1, K2 inverse, right? And this right here is representing a left coset, right, in H, okay? Because X is any element, some element in G is actually K1, K2, but we know it's in G. And so that's representing a left coset. So what that tells us is that there exists, because H, since H is a normal subgroup of G, there exists, let's say, an H prime in H such that X H2 inverse equals H prime X. Okay. And if that's the case, hopefully that makes sense. And if that's the case, I'll do it underneath. If that's the case, then we can rewrite, let's call this star. Then star now is going to become what? H1, H prime, X, which is, now we can replace that back in, K1, K2, and this is the element in H, K, because of closure. So we are done with our proof, and I will see you in class.